You don't want to miss this. This session is entitled, as you see, The Self-Driving Network. Our speaker is Dr. Kireeti Kompella, and he is Senior Vice President and Chief Technology Officer for Juniper's engineering team. Before taking on his current role, he served as CTO at Juniper Networks. Previously, he was the CTO at Contrail Systems, which was acquired by Juniper in December of 2012. Prior to joining Contrail, he was CTO and Chief Architect Junos at the Juniper Networks. He has deep expertise in packet transport, large-scale MPLS, VPNs, VPLS, and layer 1 to layer 3 networking. And at heart, he says, he's still an engineer and a coder, and he holds 46 patents. And I had I had a great time when we had an executive session at Juniper with their CEO and Kireeti and others, and listening to him give this presentation on what automation is going to mean for the networks that we run. And it was just so wonderful. And just the day afterwards, I wrote him and said, "Would you come to our conference and talk to our community about this?" So without any further ado, Kireeti.
Thanks, Louis. Yeah, it's a really big honor, and I'm going to tell everyone I keynoted at CENIC with windsurf. So it's like that's going on my resume. But thank you, Louis. It's really nice to be here. I will say I stepped out for a few minutes during lunch, and it's beautiful out there. So I will hold it against you if you leave my talk. But if you all leave, I won't hold it against you because I will join you. Yeah, I'm going to talk about SDN. It's just a different SDN than you think of, self-driving networks. So when I first gave this talk, it was almost 3 years ago. So some of what I'm going to tell you in the next few slides you've seen, and we've a lot more exposure to it now. But when I started, it was newish. This is the original. Well, this is a V2 of the first car, modern automobile. This is a Benz patent motor wagon. Almost 130 years ago, or actually a little more than that. Very, very, very manual system. And we've come a long way since that. So we've added a lot of automation to vehicles. We've made it much easier, much safer, much more convenient to drive, especially if you want to go long distances. So these are all really nice innovations. Some of them have been really tough. And the question is, are we done? Do we just have these incremental stuff, or do we actually have something fundamental to change in how we drive cars? And so we do. There was a grant challenge by DARPA in 2004 saying, can you build a fully autonomous vehicle? So the goal was to do this stretch in the Mojave Desert, 240 kilometers, 160 miles. And there were about 25 teams. They did offer a prize. It was $1 million. It was helpful. But there were about 25 teams, and they failed. They didn't even make it 5% of the way. But they tried again in 2005. They upped the prize to $2 million. That's nice. And 5 teams finished. And then and that's on a freeway, no human drivers, only robotic cars. In 2007, they did the challenge again, but they call it an urban challenge. Only 96 kilometers, but with traffic signs and other human drivers. And again, 5 or 6 teams did complete this. So in the space of 3 years, there was a huge progress in the ability to have a car completely drive itself. And of course, at the time they did this, they didn't fully realize, well, it's DARPA, so maybe they did, but they didn't fully realize what the impact of this is. In terms of, I don't need drivers anymore. I will need programmers. I'll need people who can build these systems, maintain the systems, enhance the systems. I may not need cops, traffic policemen, lawyers, witnesses, and all this, because I have so much telemetry with these cars now that, you know how at traffic lights at some of the major intersections, you have one camera or a couple of cameras. But now every car has, the Teslas have 7 cameras. And so, you have so much telemetry. There's a study at a university that said without changing the physical infrastructure of highways, you can put 4 times as many cars on it. What happens to ambulance chasers? Maybe you don't need them anymore. They're seriously thinking that you'll have far less accidents with these systems. And then there's this whole other issue of ethical self-driving or ethical cars. If you are in a really bad situation and you have a choice between killing an old man or killing 5 young school children or killing the passenger, which one do you pick? And for those of you who are existentialists, this idea that you choose not just for yourself but for everyone, well, that comes true here, because when you code it in the car, you're not making a one-time, on-the-spur-of-the-moment decision. You're deciding for everyone. So it becomes a really big issue. And of course, at the time that I did this, Uber had just started trialing self-driving cars in Pittsburgh. So randomly, if you look for a ride, you'd get a self-driving car with 2 people in it, because you had the driver just in case, and you had the person who was overlooking the AI, and of course, you have the passenger. So you thought you're going to get a car with 0 people in it, and you actually got a car with 2 people in it. But that was just for the trial. So we've moved on to this Google car, which is actually should be Waymo, which has no steering wheel and no pedals. So we've come a really long way. And this thing drives at a top speed of 25 miles an hour, but it doesn't have anything in it. And so this is not an incremental improvement anymore. This is a huge step forward. And what I live not too far from where Google is, and I see a lot of these cars in my neighborhood. I think our little township had a contract with Google. You can come and drive anytime you want. But I'd see them like 4 or 5 times a day, and I'm just driving to and from work. It's huge. And now, people are saying we'll have commercially available self-driving cars. So I'm thinking, here there's this car that's completely driving itself, and it uses the network to get there. But the network that it runs on is manually operated. What's wrong with this picture? So this is where I said, no, we got to do something better. So I suggested a networking grand challenge. Build a completely self-driving network. It self-discovers the components. It creates the topology. It automatically comes up with the basic configuration. It figures out what services are needed and connects people into the network. It monitors itself. It produces a report saying, this is how I'm doing. It can, ideally even predict, this is where I need new capacity or new bandwidth. And the result would be to free up people to work at a higher level, to think about what we want next in the network, instead of being in the daily grind of typing away at the CLI. One of the bigger things is in the network, we usually have already put in place what happens if something fails. So we have what in my previous life as an MPLS guy, I would call fast readout. If this link breaks, this is how you'll go around it, and so on. So events in the network are generally not, they don't need immediate response. They're not immediate emergencies. But a security breach is. And the faster you can detect a breach analyze it, figure out how to remediate it, and stop the attack, the better off you are. So I think that's one place where having a machine behind the scenes figuring out what to do and doing it is really helpful. So the way I would put the challenge, I don't have a freeway to drive on, but a self-driving network at the edge of the network where you offer services to your clients, where you can monitor those services and you can be proactive about them and make your service better, make your service responsive. I think that would be a place to start. Now, you can do it in the core. I think the core is a little more boring, and it's a little harder for the CFO to see the value in this. And we always have to get the CFO looped into this. And you can go further. You can get to the point where you understand your customers. You understand how they use the network. And you can do that from 2 points of view. From a defensive point of view, this customer, whether it's a human being or whether it's a server running an application or an IoT device, this is how they normally behave. They're behaving differently. So let me examine what that is. Or it could be proactive. It could be, this is how the customer, this is how the client uses the network. So let me prepare the network ahead of time, knowing that they're going to put a big burst of traffic in it, or they're going to look for a low latency path, and let me prepare that for them. And this is a far cry from asking them, tell me how you want, what do you want from the network? Rather, you analyze how they use the network and you're responsive to that. The impact of this, you need a very different skill set. You still need the people who are what we call JNCIE, Juniper Network Certified Internet Engineer, or CCIE, or whatever. You need people who know the ins and outs of BGP and ISIS or OSPF. But you move on from that to, I know BGP policy, but I want to make sure my AI is implementing the right policy. So how do I tweak the AI to do what I need it to do in the network? If it's behaving well, fine, but if it's not, how do I nudge it in the right direction? I go from configuring a service, I need a VPN here, I need a pseudo-wire here, to what kind of new services should I design? Because if I just come up with this new design, the network will implement it. I go from being reactive to proactive, so I don't always wait for something to happen and then say, oh, this is how I'm going to respond, but I actually get to the point where I can be I know my customers well enough that I can actually do the right thing. And then maybe we change how we think about security from putting the right ACLs, the control lists, to having the system say, this is normal behavior, this is an anomaly. If I detect an anomaly, I'm going to send it through maybe a DPI engine, say, oh, this is what's going on, I need to stop this, or no, this is actually fine. I need to treat this traffic as benign. And possibilities. I won't put anything up in front of you. I'll give you a few crazy ideas. But this is what I would like you guys to think about. If I had a network that would configure itself, and not just configure itself, but run itself, how would I think differently about building networks? One of the ideas that I thought of is I visited NTT in December of 2015, 5 years ahead of the Olympics. And NTT and KDDI and all these Japanese carriers are already thinking about how they would plan for it. I mean, what they would do, and they were planning for this, more bandwidth that they need, and what venues do they need to put all this bandwidth, and how would they think about it? 5 years ahead of the Olympics, they're thinking about it. And I'm thinking, if you had a truly self-driving network, you say, oh, it's Friday, the Olympics start tomorrow. You dump a bunch of equipment onto a self-driving truck, and it would drive itself to the venue and disperse all this equipment, and the equipment would figure out where they should be in the different stands and in the bleachers, and then configure itself, provide the service, realize that there's a group of people here really, really active on Twitter, so I need to put more bandwidth here. And here are guys, old-fashioned people who are actually watching the races. But figure that out in real time and adjust all this. And then you come back 2 weeks later, pick up all the equipment, dump it back on the truck, and go off to the next venue. Very, very different from what you're doing today, which is 5 years ahead of the event, planning and wondering where to put the equipment and what kind of fiber and stuff like that. So I think we could think about building networks in very different ways. We could think about, spikes in network usage in many different ways. At the same time, and I was having this conversation at dinner yesterday, we have to be cognizant when we as technologists, and I love being a technologist, but we're not always cognizant of what it is we're building and what is the impact of this. One thing I will mention to you is that the US Congress, so we have cities and we have states that say self-driving is okay in this state or in this city. But the US Congress is like, we should have self-driving all through the US so we can progress much faster and much further with this. And they said, yeah, self-driving cars, but not trucks, because trucks are a livelihood. And so when we do stuff like self-driving and AI and more and more automation, we don't always look at the consequence of what we're doing. So not only does the skill set change, but people may lose jobs. Now, so far, we've always had people lose jobs. We get new types of jobs. But we have to be cognizant of that. Okay, so how do we build this? Is this just a pipe dream? Yeah, probably, but don't tell that to anyone. There are 5 technologies, I think, that are really important. The first is declarative intent. What do you want? Not how to do it. Today, we're very focused on how to do it and what's the right CLI command in Junos or iOS or EOS or whatever your favorite OS is. How do I have the right data for this? What's the big data that I need for networking? What do I do with all this data? Correlation. Of course, automation, and then decision making. So I get all this information, I correlate it, and I figure out that I need to do this. What is it that I need to do, and how do I make it happen? So to illustrate declarative intent, let me go back to the Waymo car. You get in, there's no steering wheel, there's no pedals. What do? You have a little screen that says, where do you want to go? And I'm just making this up because I've not actually been in one of these. But I figure it's something like this. So you say, I want to go to the airport and I'm running a bit late, so get me there very quickly, or I don't want to pay tolls, so find a route that doesn't have tolls. So you say where you want to go, but the question is, do you even need to do that? And this might get creepy, but imagine that the car reads your phone and says, oh, you have an appointment in Starbucks in 15 minutes, I'll just take you there. Or even more creepy, every day you get in the car and you go drop your daughter off at school, and then you go to work. So when you get in the car the next morning, it says, do you want to go to school? I'll take you there. And then, okay, now do you want to go to work? I'll take you there. So it can learn your habits. So, you start with intent. I will tell you what I want, but then you get to the point where the car says, I know what you want. And I might know what you want by reading your phone or by knowing what you've done for the past 6 weeks or whatever. So, yeah, that's basically, make it happen. Or, for those of you who are Star Trek Next Generation fans, this is number 1. You tell number 1, make it so. He goes and does it. Riker. So we have products with intent. If you look at Contrail, you think of Contrail as a data center SDN, but it's really about intent. These are the virtual networks I have in my data center. This is the interaction between the virtual networks. This new VM belongs to this virtual network. Make it so, right? And if the VM moves from server 1 to server 2, take all the policies with it. And whatever the policies are for connectivity, for QoS, everything goes with it. So if you think about it, it's really about intent in the data center. And we have another product called Northstar, which is about WAN connectivity. And again, if you think about this is about how you express your intent for connections across the wide area. So what kind of bandwidth do I need from point A to point B? What kind of resiliency? What kind of, whatever. And you just state your intent and boom, it happens. So we do have intent. I don't know, 6 months ago, the CEO of Cisco said, intent will change networking for the next 30 years. Yeah, it's already been changing the networking for the last 5 years. We just haven't put it wide enough in the network. But we have a start on this. So I'll skip through this. I kind of talked through this. But essentially, I look at intent as you specify what you want at a high level, and then you compile it down to actions in the network, whether the actions about VPNs or the actions about LSPs or whatever it is. Okay, the next thing is telemetry, and I look at this as big data for networking. And in the old days, you used to ask the box, how are you doing, and what are the statistics on this port, and what's going on with this VPN, and you keep asking, the polling. The one thing that comes to you is traps, but everything else you ask the box, and that's just so old-fashioned. So what we have now in place is a system where you tell the box, give me the statistics on this port every 5 seconds, and boom, the statistics flow to you. So you get them in real time, you get them at a very much finer granularity than you could otherwise, and you get them with much higher accuracy. And we call these sensors, and we keep adding more sensors to this. So we start with ports, we start with statistics on LSPs, but we keep adding to them, and people say, yeah, we could use a new sensor of this kind. Correlation, analytics for the network, which is, take the data that's in the network. So if you think about it, you've got BGP information, you've got IGP information, you've got the users, and they have different kinds of statistics. You've got flows in the network, and you've got this path. And if you get flow data, you basically get a source IP, a dest IP, a source port, a dest port, and like, yes, so what? But if you start correlating, you could say, oh, this source IP, look at DHCP, yeah, it's this customer, it's this client. This destination IP is from this peer, and this is the path across the network. So you suddenly turn this bunch of numbers into something meaningful. It's this, well, for you guys, this science center, this lab, talking to this other lab, going across my network, across this path, and this is why I should invest in this path, or I should put more bandwidth on this peering point. Automation. So this is kind of a diagram of our operating system. But the thing that I want you to focus on is the stuff on top, where we talk about the different ways you can automate things on our OS. So you've got Python, you've got Ruby, you've got Salt, SaltStack, Puppet, Chef, Ansible. Pick your favorite way of automating things. We probably have it. We also have something called NetConf, which now more and more people are using. I was just talking at lunch with someone from ESNet who says, I don't want people poking at the CLI anymore, which is fine, but then you need a way of talking to the box, and so NetConf is the way you should go, and everyone's going in that direction. And finally, you have decision-making, and decision-making is about, something happened, what do I do in response? What are my choices, and how do I make that decision? Well, you can do this via rules, and that's an easy way to start. And you say, if I see this, I'll do this. So there's this thing for IoT programming called if this, then that, IFTT. So if you see this, do this. If you see this, do this. And each of the rules is really simple, but then you say, oh, there's this corner case I didn't take care of. Oh, there's this other thing that'll happen. And the rules start overwhelming you. Even though individually they're really simple, you get so many of them, and you like, have I dealt with all these corner cases? So the other side of it is machine learning, which is really cool, really powerful. Nobody has a clue how it works. And literally, that's the case. So you give it 1 million pictures of things. So here's a cat, here's not a cat. Here's a cat, here's not a cat. And 1 million pictures later says, I will tell you cats from not cats really, really well. And you ask, how did it come to that conclusion? No idea, but it does it really well. So there's a really nice article in the New Yorker in 2014 called Autocorrect, which is the story of the first self-driving car from Google. And they tried machine learning. Well, they first tried rule-based systems, and they tried machine learning. And they finally said, we need both. And I think we will need both in self-driving networks as well. The rule-based stuff here are the things you don't do. You don't kill a pedestrian. You don't, you don't kill the connectivity to my customer. And here are the things that you learn. You just go through it. Have enough examples, and you figure out how to do it. So what kind of decisions? Well, since I'm focused on the edge, I'm going to talk about service placement. And service placement is if a customer comes to me and says, I want a pseudo wire or I want a VPN, and that customer can be connected to 2 or 3 different edge boxes, which box do I place them on, which interface, which port, which VLAN? And today we do this in a very static way. And I think we're still in the 20th century. We need to move on. To illustrate this, I'm going to give you a rather difficult analogy, but bear with me. So what you see here is compute orchestration, compute virtualization. On the left, you see compute virtualization. This is before virtualization. You have dedicated servers for your different applications. So you have a finance server, you have a database, you have a web server, you have some other applications, and they're dedicated on these boxes. Do the boxes look similar to you? They by and large are. There might be a little more disk on one, there might be a little more memory on the other, but they're basically, compute servers, Intel probably, x86. And on the right, what you see is dedicated boxes for specific services on the edge. So BNG or CMTS, more applicable to telcos, but peering boxes or business edge, VPNs and pseudo wires. So people have dedicated boxes. Even though it's physically the same box, you have multiple instances of it. And the question is, what did people do differently in compute? Well, what they did was they separated the disks out. They put them as network-attached storage. And then they said, your applications are going to be VMs running on these servers. And where the VM lives is not based on, this is the server for database and this is the server for finance. Where your VM lives is based on what's the machine, what's the server that's best suited to the application right now. And so you have the same thing on this side. You have a bunch of network devices. These are not VNFs. These are PNFs. They're physical network functions. But the devices are much more fluid, or the applications are much more fluid on the devices. So it's not the case that the device on the left is a subscriber device. It just happens that the subscriber is there right now. But if you think about what virtualization truly means, it's separating the applications from the physical instantiation. So it's not, I have to run this on x86. It's, I have to mentally separate these two. So if you look at this, in compute orchestration, you have this thing called vMotion, virtual motion, where you take a VM from one server and move it to a different server so you can redeploy the server for something else. Or you take, you move a server, you move an application away from a server for maintenance. Well, imagine that you do the same in networking. In real time, you move subscribers from one box to another, and you move services from one box to another, so you can upgrade them or redeploy them for something else. To do that, you need this thing in between that basically allows you to move your storage, to make your storage available everywhere. Well, here you would need a switch. It could be a layer 1 switch, it could be a layer 2 switch that decouples your customers from the boxes that offer the service. I'm not talking about using x86 for this. I'm talking about, not mine, right? Yeah. I generally try to put it on mute, but I don't always remember. I'm talking about getting that same, the way I think about virtualization is freedom from physics. And I know a lot of you people do physics here, so don't throw things at me. But this thing that I'm stuck to this server for a particular application needs to go away. And so you don't have to go to x86 for that. What you do have to do is have a much more dynamic way of assigning subscribers to services. And that would be really hard to do if you don't have automation behind you. And ideally, you actually have some very high level of machine learning or other decision making to make those decisions in real time. So, okay, so I've talked about self-driving networks in the abstract. What does it really look like? Well, it's basically this closed loop architecture. You've got telemetry coming from the network, you process that, you make a decision, and you put it back in the network. So it's this closed loop. And I want to emphasize this. It's not about zero-touch provisioning. It's not about a one-time, I'm going to start up the service right. It's about the life cycle management of a service. And the reason why I say it's nearly closed loop is it's driven by your intent. So you have to tell the network how you want it to run, what to optimize for, what to emphasize, what to de-emphasize, what kind of actions to take at a very high level, but you have to inform that. So if you're talking about peering or cloud, you might say, I have connections to these two clouds, which one do I pick? And I might want to pick based on the cost of compute in this cloud versus that cloud at a given time. You might pick that based on latency in accessing the cloud. You might pick that on security, whatever your process is. But you have to make those decisions. And ideally, you don't make these decisions statically. You don't make these decisions, in a sticky way. But you can actually be much more fluid about that. And to do that, you need real-time telemetry, both about what's going on in the network as well as what's happening from the customers that are feeding this. Security. As I said, security is one of the things that you have to be very, very fast about. You have to identify threats very quickly and take the right remedial action. And in the world of IoT, if we think about 1 billion devices or more coming onto the network, usually they're also very weak devices. They don't have enough CPU and memory to run security. You need things like these IoT gateways that will say, this is a normal behavior of this thing. So for example, here's this video, the baby monitor, that maybe goes out to a DNS server once a day to make sure it's talking to the right server in the cloud. And if it starts going out to the DNS server once every second, there's something wrong. And that should be really obvious, except we had a major attack on our DNS servers because we didn't think about this. So should we put in the rule that says this IoT device should go out to the DNS server once a day or once an hour rather than once a second? We can't think of all the rules. We can't think of all the different ways people are going to attack the network. So rather than trying to put the rules in place, if we did behavioral analytics, we said, this is the normal way that this thing behaves, it's deviating from that. So let me analyze why it's doing that, or let me just take remedial action and then alert a human to actually take care of it. So this is how it might look. You have an endpoint, and it behaves in some way. So you say, okay, who are you talking to? How often are you talking? What kind of packets do you send? You're doing something different. You're talking to a different server. You're sending more packets. You're sending less packets. Let me figure out why, and then let me take remedial action. So rather than putting all these rules in place, imagine that you had machine learning in the background saying, this is normal behavior, this is not, so let me take some action. Or that's more defensive, this is more proactive. Here's a customer, this is their bandwidth. At this point, they're now starting a backup, and because you've rate limited the customer to this, their backup takes a long time, but you know every morning at 4 a.m. they do this backup. So maybe you say, okay, I'm going to change the QoS policies, I'm going to change their bandwidth limits. So, and you don't tell me ahead of time, at 4 in the morning you're going to do this backup. You just learn the behavior. And then you say, okay, you'll have a higher limit at 4 in the morning, and your backup finishes in an hour instead of taking 4 hours. If you're not creeped out, you should be, but this is what big data is about. And yeah, use it for good, not for evil. No. I'm just going to leave it at that. So I'm just going to step through this. There are 5 stages of self-driving as defined by the the National Transportation Safety Board, NTSB, something. And basically, you start from, I'm completely automated, I'm completely manual, to I'll do some of the functions, to I'll do more of the functions, to I'll do most of the functions, but you need to take over once in a while, to you don't need to take over. I'll just take care of it. So this is kind of the trajectory for self-driving cars. This is a difficult trajectory for one reason, that in this mode where I have high automation, the car says, I will drive most of the time, but once in a while I'll fall back to you and say, take over. And what are you doing? You're daydreaming, you're watching Harry Potter, you're doing something, and you die. It says, no, it's not funny, it's happened. To ask a human to switch context, to go from reading a book or doing something else to actually taking over and driving, and to do it in the space of milliseconds is a really hard thing. To do this in networking actually is a fine thing to do. And I think we will need to do that. So let me walk through this. We start with some manual networks where you do a lot of things with CLI, but you start adding a little automation to it, and then you start getting to finer grain telemetry where you can actually start making some decent decisions. And you get to fine grain motorization or automation of different functions. For example, you have more visualization, you have resource monitoring. You don't necessarily take action, but you say, let me automate some of these things and report out to a human to take care of it. I'm going to make much more deeper decisions about the network to the point where, so we have this thing called EDI, event-driven infrastructure. We actually prefer to call it JEDI, Juniper Event-Driven Infrastructure. But that's an example of good marketing from Juniper. I'll give you an example of bad marketing soon. To the point where you have a lot of closed-loop processes in the network to eventually, I can do this all completely automated. Now, I think in cars, you need to get to this point, step 5, where the car is completely autonomous. But I think in networks, we can live here for quite a long time. And my animation is really broken, but basically, you're probably somewhere there. Some people are more advanced, but we need to get to at least here, where 90% of stuff that needs to happen in networks is done automatically. So, as I said, there's this closed loop, and this is the basis of self-driving, whether it's for cars or for networks. But you could break that down into a set of smaller loops, and these loops are much more tractable. So we call these bots, and this is where marketing, I don't think, really worked well. But anyway, think of it as a good bot. So a bot may be a closed loop, or maybe I'll do some of the processes and then hand it off to you. So what are some examples of bots? Well, if you look at cars, you talk about completely autonomous cars, but then you look at, okay, autonomous gear control, autonomous speed control, like your cruise control, staying in a lane and parking. Okay, and then you build from that and you get to the point where the car will actually drive itself. So can we do that in the network? Well, you can start with service activation. So someone comes onto the network, you say, oh, I know this person, this is a service they signed up for, I'm going to give them connectivity. It might be, just about bandwidth, might be about, oh, I have to place them in a VPN. And that VPN is going to run over this LSP, but I have another sort of closed loop that manages the LSPs and says, I got to balance these, I got to put more bandwidth here, I got to put less bandwidth there. And then I have SLA assurance, and I have peering. But you can also see these three can interact. So I did the service allocation. I put them over this LSP. I looked at SLA. Oh, it's not really working well. Maybe I go back and say, I need to put more bandwidth on this LSP so that they get the service that they should be getting. Or maybe they're peering with someone, so I need to balance the peering out. So we have this bot library that we're building, and I'm going to stay with the word bot for the moment. Basically, a number of different types of bots. And initially, we got 4 kind of ready to go. Well, not quite ready to go, but in the first half of this year, we should be seeing them. One is a health bot, basically monitoring things in the network, looking at key statistics and saying, hey, the routing engine, the control plane for this router is running out of steam or running out of memory, or this line card seems to be having some hiccups, or this transponder seems to be suffering. The bit error rates are going too high. The next one is this peering bot, which is really about you state your intent for peering. I want more traffic going to this peer, or I want a path for this particular application that has a lower latency. So which peer do I choose for that, or stuff like that. So you speak at a higher level, and it translates to BGP policy. To a network slicing bot. So we have this new feature where you can take a physical device and say, no, it's actually 3 routers. And each of the routers can run their own version of the OS, and they can talk to each other via the backplane, so you're not actually burning front-facing interfaces for talking between them, but then talking to other things. And managing the slices, could be non-trivial, but we have a bot to help you with that. And we have a bot for broadband, which may or may not be interesting to you guys. So I did race through some of these slides. I did want to leave time for questions. But before I close, I want to talk about the benefits of having a network be self-driving, which is, first of all, you talk about what services you want on the network at a much higher level. And I think this was the real intent of SDN. We got kind of hung up in the machine language of SDN, which in the old days was OpenFlow, and now it's P4. But this is really machine language, how you implement it. But we really need to talk about how do I interact with the network? How do I tell the network what I want, what my customers want from the network? The next thing is I want end-to-end service management. So I want to be able to look at all the aspects of service management, from provisioning the service to placing it over whatever your favorite underlay is, to monitoring, to taking to remedial action. I want telemetry-based service placement. So rather than place this customer on this device, I want to know that device is really busy right now, so I should pick a different one. The same way as when you say, here's my VM, and I need 3 virtual CPUs and 16 gig of memory and 1 terabyte of disk. You don't get to pick, if you're going to a cloud, you don't get to say, and I want it on this server, in the 6th aisle and the 4th rack. You don't get to say that. You get to say, I want 3 vCPUs, 16 gig, and 1 terabyte of disk. So can we get to the point where we specify what we want from the service and the placement gets done in real time by picking the right server? And then network server. And once you do that, in real time, move people around. And for those of you who are in a NOC, a network operations center, you should be scared. Because we're talking about a customer that's connected to this device being moved in real time to a different device because this device is having some hiccups or having too much congestion or whatever it is. And to do that in real time is something that would scare us today. But if it's automated and done the right way, this is how compute orchestration is done. We need to bring that to networking. And finally, matching the underlay to the services required of the underlay. So if we can do all these automatically and we have a self-driving network, we will realize these benefits. Okay, so I think we need a vision in networking that goes far beyond what we're doing today. I think we tend to be a little scared. Now, I think R&D networks are different. I think that you're a little bolder. You were much more out there when it came to things like OpenFlow and SDN. So I think we need to be there and we need to try new things. One of the things I'm really high on is machine learning, but I don't want you to think of this talk as a talk about technology. It's a talk about an end goal that we can aspire to, and then we take these baby steps. And at some point, we'll realize we're going down the right path, or we're not, or we have to adjust. But we need a vision to aim towards, and I think we need to be really bold with that. There's an economic imperative for this, and everyone tells me as a vendor, hey, your boxes are too expensive, but actually your OpEx is probably higher than what we charge for boxes. And I know that that's the case with telcos. Their OpEx typically is 2 or 3 times what they pay for the CapEx. There's a skill set imperative, and I was talking to people today about hiring and finding the right set of people with the right skill set, which is you need to know networking, you need to know BGP and OSPF and ISIS, you need to know Junos and iOS and whatever, but you also need to have maybe Python skills or Java or whatever your favorite language is, and you need to do some more automation. And security. So, yeah, that's my talk. Unfortunately, I left time for questions. So, anyone? Yes, Glenn. Yes. Do I need to repeat the question? So where do I see the service edge? Where is it today, and where do I see it migrating? So for me, the service edge is at the end of the layer 3 infrastructure. But unfortunately, that's not the true service edge. If you look at a telco, they have layer 3 infrastructure, and then they have layer 2 infrastructure, typically in the metro. And they're slowly beginning to bring the layer 3 infrastructure further out. So the service edge is as far out as you can go. And one of the indicators of that is this thing called what used to be called mobile edge computing, which is now just edge computing, where you're saying, in my central office, I'm going to put servers. And maybe even in my base station, I'm going to put some amount of compute. And so we're looking at pushing the services, starting the services even earlier. So it's not like you enter the network, you go over maybe layer 1 circuit, or you go over some Ethernet for a couple of hops, then you hit a box where you get your pseudo-wire, or you get your BNG, or you get your VPN. They're saying, can I push that further out? And I think that's a really good idea from multiple points of view. If I have a more distributed service edge, I have fewer eggs in one basket. So if I push, for you guys, if I push my service edge on campus rather than backhaul it from the university to some more central point, maybe I can aggregate 3 or 4 universities there. But if that box went down, 3 or 4 universities are going to come after you. So if you can actually say this is on campus, it makes the number of endpoints you manage higher because there's more of them. But again, if you automate it, it shouldn't matter so much. But if one of those boxes went down or you had some kind of issue with them, there are fewer people behind it. So so this is not just in networking, even in compute. There's a video from A16Z or A16Z, which is Andres and Horowitz, from December of 2016, called The End of the Cloud. And they're trying to be provocative. But he says, the cloud is over, we're moving to distributed computing. It's a pendulum, and we keep swinging. But I think for services, the further out you put them, the better off you are. And it's the end-to-end principle for the internet anyway, push it out. So I think it's a little further in today, but it needs to be further out. Yes? You want me to get in trouble? We did autonomous networks for a reason, to separate domain of control and stuff. And this makes this very difficult. But the idea of a self-driving network consisting of multiple, so I have this big loop, but it consists of multiple smaller loops. It could be that each domain has its own loop and says, I'm going to manage from the LHC collider to this point, and then from there, I'll hand off to you. And maybe at some point, and this is the other thing about SDN, we were so focused on the southbound, we need to focus on the northbound, which is how do I specify what I want to the SDN. But we also need to focus on east-west. How does my SDN talk to your SDN? And what is the handoffs? And how does my learning of whatever happens in my part of the network interact with your learning? I will say that I think it's in CERN that they have, I don't want to say they have, but I saw this about a year and a half ago, an effort for a self-driving network. And I'm not sure that they used that exact phrase, but they wanted a completely autonomous network. So maybe we'll start there and then it'll come to the rest of us like everything else does, like the World Wide Web. But yeah, we have to talk about how you hand off, because you don't want one entity doing everything. It's just a bad way of doing things in the first place. Plus, everyone wants their own autonomy. So we have to figure out how my self-driving network interacts with yours. And that's why we talk about peering a lot, because that's the edge of my network. And if I can get my peering right, and I can hand off to you. But I don't have a better answer than that, sorry. Anyone else? Cool, thank you.